Hello everyone, this video is going to show you how to construct a dual mode resonator based on the Microstrip implementation. In the last video, we have shown you how to construct the single mode resonator using the ideal transmission line, and also we play some trick to achieve a dual mode resonator response by simply adding a shunt inductor at the midpoint without additional length added to the transmission lines, which means the overall size was not changed, and we are able to achieve a dual mode resonance as shown in this graph here. So just to recap, now I remove the inductor as well as the ground. So here we still have 180 degrees transmission lines. So here we form a single mode resonance response. So we added the inductor, shunt inductor. So now we form a two-pole resonance response. So what we're going to do now is we're going to replace all these ideal transmission lines with the actual implementations based on the Microstrip. So we can go to the toolbox under the Microstrip category, and we can drag in the emlint, which represents the Microstrip line. So here you can see there are two attributes that the user have to insert, which is the width of the line and the length of the line. So how to calculate the width and the length of the Microstrip is pretty simple in the EDS. Here you just have to define the operating frequencies, which is 1 gigahertz. And we already know that the characteristic impedance of the line is 50 ohms. And we want to have electrical length of 90 degrees. So we have a pretty fast synthesis tool, which helps you to calculate the width and the length in an instant. So here we have worked out the width and the length. Of course, all these calculations are based on the substrate definitions that the user have to prescribe. You can go to the setting page and look at this the transmission line options. So we have a few of them. So we can realize the transmission lines using Microstrip strip line, subspectrum strip line, or the rectangular waveguide. So here, the Microstrip, we have chosen these definitions. You can modify these parameters according to the actual substrates that you've chosen. So we go back and we just replace the ideal line with the Microstrip line. So now if you click on the simulation button, it should give a two-pole response. So now you can still observe the two resonance pretty close to each other, and you can achieve like the return loss at the minimum of 16 dB. However, you find some significant loss at the passband of 1.64 dB insertion loss. This is basically due to the loss tangent of the substrate, as well as the finite conductivity of the copper that we define for the Microstrip. So, of course, for the inductor, it can be also replaced by a short circuit stub. So having a very small length of short circuit stub is a very good approximations of inductor at high frequencies. So similarly, we drag in the emlint. So here we define the frequencies, which is 1 gigahertz at the center. Let's assume that it has a 50 ohms characteristic impedance, and we want a very short transmission line at one end shorted to ground. So for example, we put electrical length of 1 degree. So the corresponding length of the line is 610 micrometers. So now we simulate it, and you can see like it seems to be a single pole resonance. In fact, it is a two-pole response. Basically, the two resonances are too close to each other, so they are overlap. So let's say we increase the electrical length to 1.5 degree, which corresponds to 914 micrometers. So what happens now? You can see the two resonances are well separated, and we can still achieve like 14, close to 15 dB of return loss at the center, and still the passband loss increase slightly from 1.64 to 1.667. This is again due to the loss of the transmission lines. Previously, it was ideal inductor. So having this kind of simulations with the actual implementations and the substrate definitions will give you a much more accurate results, which are very close to the actual design or actual product performance. So you can have a very predictions of your performance before the design are being fabricated. Of course, you can find also the center frequencies are being shifted slightly to 0.9 gigahertz. I think this was explained in the last video. It was due to the fringing, the capacitive coupling from the input and the output to the resonator part. So some couplings are being absorbed into the resonators, causing the shift of the center resonance to the lower side. So here ends the part 2 of the microstrip realizations of the dual mode resonators. I hope you enjoyed the videos and learn new things from this video. Thank you very much.